Hi, I'm Callahan-Flintoft, and today I'm going to talk to you about the attentional drag. So the brain has this ongoing problem that it needs to solve. Imagine you're driving down the road. Not only do we attend to objects in space, but there may be particularly task-relevant windows in time that we want to select as well. To lay this problem out in discrete time steps, imagine we have time going down the side here. We have our first couple beginning frames, and then we have our critical moment where we need to not only shift and engage attention at the target location, but then to quickly disengage so as to not include subsequent irrelevant information in our selection. To study this in the lab, we often use rapid serial visual presentation, or RSVP, where discrete stimuli are presented sequentially. For instance, we might present participants with two streams of letters and ask them to report the letter presented at the time of the cue. And what we find is that participants are highly accurate with a selection latency of under 25 milliseconds. However, information doesn't always abruptly onset. As a simple example, if you were monitoring this clock face, the object appears to evolve over time rather than being replaced by a new object at each time step. This is temporal autocorrelation, where the feature values of an object are related to themselves in time. And going forward, I'm going to refer to temporally autocorrelated as smooth. To demonstrate how this would look in an experiment, this is an example from Carlson and colleagues where your task is to remember the clock face configuration at the time the rim flashes red. So here was the actual clock face that was presented at the time of the cue. If you got that, well done. But more likely, you're like the average participant in this study who selected the configuration presented over 150 milliseconds after the cue. So we have smooth displays measuring selection latency as over 150 milliseconds, while RSVP is measuring it as under 25, which led us to wonder if a feature's temporal autocorrelation affects its selection latency. To test this, our first experiment had participants monitor two changing color disks. The disks either changed smoothly, 16 degrees around the color wheel every 108 milliseconds, or randomly. Importantly, the SOA was the same in both conditions, and these trials were intermixed within block. So now I want to give you a feel for how this went. I want you to remember the color of the disk when the white ring flashes around it. In case you're curious, this was the color at the time of the cue. And for completeness, let's do a random trial. Remember, you're going to report the color of the disk at the time the white ring flashes around it. And again, this was the cued color. At the end of every trial, participants are presented with a report screen where they move the mouse horizontally to update the test disk and then click when they find a color that best matches memory. This gives us a reported value which we can then compare to the true values presented to calculate an error. Doing this for every trial and every subject gives us a distribution of serial position error. Here are the results for experiment 1. So critically, what we're comparing here is the difference between the average selection latency and the time of the cue in both conditions. And what we find is that selection is delayed by over 100 milliseconds in the smooth condition compared to the random condition. And this was replicated in a second sample as well. So if our argument is that smooth feature change increases the selection latency, then by extension, if we increase the smoothness, we should see an increase in selection latency. And so in experiment 2, we do just that, where we have the same smooth condition as before, but this time we're going to intermix those trials with smoother trials, where the color changes 4 degrees every 27 milliseconds. So importantly, our rate of change is the same. We're just manipulating the granularity of the steps. And as predicted, this increases the selection latency. And this was replicated as well in the second sample. Together, these experimental results led to the development of the attentional drag theory. To give you a broad strokes overview, let's remember the task where you must select the color presented at the time of the cue. So if we plot the stimulus input coming into the system over time across the bottom here, the presentation of the cue will trigger the deployment of attention, opening an attentional window in time. Now in the random condition, the feature transient presented after the cue is going to disengage attention, limiting the colors available for report. Whereas in the case of the smooth condition, the temporal autocorrelation presented after the cue will extend the attentional window in time, resulting in later colors being available for report. A key assumption of the model, then, is that it is the smooth feature change presented after the onset of the cue that increases selection latency. However, an alternative theory could be that when the system is presented smooth feature change, it begins generating predictions on what values will come next in the trajectory. And so when the cue is presented, participants are instead reporting the predicted color, which looks like a lag in selection. Whereas in the random condition, where no such predictions are possible, participants are forced to report the color presented at the time of the cue. So in experiment 3, we had participants do the same task as previous experiments, but now, on some trials, the disks change smoothly before the cue and randomly afterwards, and on other trials, the disks change randomly before the cue and smoothly afterwards. For this experiment, we compare reports to the trajectory that would have been presented had the cue changed smoothly throughout the whole of the trial. So if participants are basing reports off prediction, we would expect later reports along the color wheel in the smooth before condition compared to the smooth after. However, what we see in the actual data is the exact opposite pattern, and this was replicated in a second sample. So the effect isn't explained by predicting a future change, but a different prediction that's sort of implicit in tuning curves is that objects will remain in some local area of feature space, as presenting a green object doesn't just activate one neuron, but a gradient. When we simulate the activation of these neurons over time when presented with smooth feature change, what we see is that activation is able to build upon itself from one time step to the next. Conversely, when color changes randomly, there is no such relationship over time, and thus each neuron is limited in their overall activation. Finally, we have the attention neuron, which when excited over threshold sends excitation down to the feature neurons, who in turn send excitation back to the attention neuron. Now, if we apply this attentional circuitry to the simulations we saw before for the smooth and random conditions, we see that the greater activation in the smooth condition extends attentional engagement and results in later presented colors being excited over threshold compared to the random condition. It could be that the visual system uses temporal autocorrelation to parse continuous information into meaningful episodes, using visual transients to make meaningful separations. And potentially, these attentional episodes might contribute to longer timescale event segmentation. Thanks so much for listening, and special thanks to my co-authors on this project, Brad Weibel and Alex Holcomb, as well as my funders.